Yeah, welcome to our presentation. So I'm going to present the paper Flaky test sanitization via assumption inference that is joint work with Sean Rashid and Amjad here from Massey University in New Zealand. My name is Jens Dietrich. I'm from Victoria University of Wellington, also in New Zealand. So hopefully it's okay to watch the pre-recorded version. So it's going to be an awkward time zone for me. I had to cancel physical attendance on short notice, so it's going to be like 3 a.m. here when the talk is due, but I will be available to answer questions. Yeah, so let me just introduce the problem with a couple of quotes. So starting with one from Uber engineering blog, a unit test is considered flaky if it returns different results, pass or fail, on any two executions without any underlying changes to the source code. It's a very straightforward, simple definition of what flakiness is. If you haven't heard about this, that might be useful. Flaky tests, as you would expect, are bad for many reasons. I don't want to go into detail here. So the same blog says, flaky tests affect developer productivity across multiple dimensions. Can flakiness be avoided by better design, better practices? Not really. It can be avoided to some extent, but not completely. So that is a Facebook engineering blog, and that's a software engineering practice, however, shows that all real-world tests are flaky to some extent. So that maybe that's a little bit of the scene for what I'm going to talk about. So where does flakiness come from? There are a couple of different sources for this, and a lot of research in the last 5-6 years has been done on this. So common sources are test order dependencies that originate from shared state between tests, like shared memory. The use of randomness or concurrency, like race conditions in the program under test, under defined APIs, like unpredictable iteration orders over containers that don't maintain the insertion order, like hash sets, or hidden dependencies on the environment where the system is executed, such as operating system, or we're mainly talking about Java here in this course, Java virtual machine version and vendor dependencies. So to better prepare what I actually want to talk about, what our contribution is, it makes sense to actually have a look into a semi-formal definition of what flakiness is. So starting from this definition of flakiness from the Uber blog, we could say that if we have runs which take tests and map them to pass or failure, that if we start having one test and different runs that return different results, then we have flakiness. And that really reflects this different results, pass or fail. However, if you have a closer look into how modern test frameworks work, it's not just about pass and fail. So there can be different states. For instance, JUnit also has an error state, and that really has to do with the oracles that's being used when in the test. So error means, there was just a failed assertion, there was some other exceptional error happening during the execution. And then, interestingly, there's a fourth state, that is a skip state. And now we can also define flakiness with respect to those arbitrary states. So in a way, we have two different notions of flakiness, and our contribution explores a little bit the space between those two different versions. The skip state really comes from here. So there's a feature in modern testing frameworks which really corresponds to precondition checks. In tests, it's often called assumptions. So for instance, in that particular unit test, let's say we have a calculator that is a local front end backed by some sort of web service that does actually a calculation. And so the test suddenly only makes sense if the network is available, so we can safeguard this with this assumption here. And if this assumption fails, then the test would be flagged as skip. So it would not fail, it would be flagged as skipped. There are a couple of hidden flavors in testing frameworks like JUnit, where basically also do assumptions, something like ignore, disable, enable on OS, disable on OS, enable on JRE. Some of them have parameters where I can actually provide the operating system where I want to enable or disable the test, and so on and so forth. But that's kind of the raw version of assumptions you have in the framework. So the semantics of this is really interesting. So that is definition from the JUnit 4 Java doc. It says a failed assumption does not mean the code is broken, but that the test provides no useful information. Assume basically means don't run this test if those conditions don't apply, and that's really communicated to the user of the test by this additional state called skip. So Going back to the original problem we try to address, and that's to tackle flakiness. Now, when you try to address flakiness in your tests, you have a couple of options where to start. And for different sources of flakiness, it's really horses for courses. You need different methods to address this. So the first one is you refactor the program. There might be something wrong in the program that causes flakiness. The second option or option group is to refactor the actual test. So you might improve the fixtures to have a more reliable test environment. You might want to weaken assertions. For instance, you might weaken assertions to take statistical variability of results into account. But, and that's the method where we focus on, you can also strengthen assumptions. And if you do this, then you have to deal with the skip state, because if you strengthen assumptions, and it's more likely that assumptions are being violated, then you get more tests resulting where the test run results in skip states. And that is where our framework comes in. We call it sufflate. And so we address flakiness by skipping tests that would otherwise fail or result in an error. Due to flakiness, we can quickly quarantine flaky tests on the fly, and instead of flaky tests transitioning from success to fail errors, they transition from success to skip, and then that means that for many build systems, builds can still succeed and go ahead, but it's still communicated to the developer or to the tester that something was wrong with this test, that they didn't succeed, but they won't stop the build. They didn't fail either. If the assumptions hold, test process as proceed as usual, and we still create in the test execution a provenance trail to inform refactoring to actually address the root causes. That overall idea actually corresponds quite nicely to how industry practice is dealing with tests or tries to deal with tests. For instance, here's a quote by Martin Fowler that was really one of the people who sparked or kicked off this entire discussion we have now around flaky tests. And he says, place non-deterministic tests in the quarantined area, but fix quarantine tests quickly. So it's really skipping tests really is the counterpart of putting them into a quarantined area. And from a GitHub blog more recently, we set out to manage the inevitability of flaky tests. So it's always flaky tests, but we have to come up with methods to deal with those. So we implemented that for one particular scenario, and that is tests that depend on network resources. There are some subtleties in there, how test dependencies on network resources manifest. For instance, it might be caused by port collisions, XML schema access for validation and entity resolution, connection timeouts, and latency issues. We found a couple of examples where that's being used, so that seems to be rather common to have tests depending on network resources. And if they do, then there are actually no good options for developers. So the first example I have here is a standard test that opens a URL connection. And it just goes with it, but if the network is not available, that test will basically fail, so flakiness will occur. So that's really the scenario we are addressing. In other projects, people are well aware of this. So the first project we saw was Chapref. It's a bibliography manager. Some of you might use this for research work. The second project is JSoup. That is a HTML parser library, quite common, quite widely used. And so they have a test like this as well with a network connection. And here they say, ignore by default, so the tests don't require network access, comment out to enable. To do, rebuild this into local Jetty server tests, so not reliant on the vagaries of the internet. So in a way, that's a pessimistic approach, but that is also bad in a sense, because even if the network is available, that test is never executed. So you get less coverage with this more pessimistic approach. So there are really no good choices. Unfortunately, it is not straightforward to put in an assumption to make that particular type of tests work by just skipping them as the network is not available. And the problem here is that we cannot just make an assumption, assume true is network available. There's no such API, and if there was one, it wouldn't be very useful because, of course, at the moment we proceed to the execution of the next line of calculator divides, the network might be gone by this. So it needs to be a little bit more subtle. We can still actually look for signals we get when the assumption we have made is violated. So in a way you could call it a dynamic assumption. So we can look for signals that indicate assumption violations even when we didn't really have an explicit statement like this to check this beforehand. The signals we are looking for are network-related exceptions. So in the tool we have built, there's abstraction. You can add more exceptions like this. But by default, we have those 3 on board. 3 Java exceptions that indicate network access problems. So the way the sanitization works with our Saflate framework is we intercept test processing and inspect the state of tests. If errors, then we look for stack traces causes related to network exceptions. If present, we switch the state to skip. If it is failures, then we look whether the failure might be caused by some exception, by some network exceptions that happened earlier during test execution. And if we find this, then we also change the state to skip. Else we leave the state unchanged and then we proceed. So tests that succeed will never be changed. Tests that fail for different reasons will also never be changed. So in a way, it's a very conservative approach. So we implemented this as a set of JUnit 5 extensions, backported it to JUnit 4 rules and to Spoke, which is a framework for Groovy and Java. There's some instrumentation, some dynamic program analysis done with ByteBuddy, where we basically look for where exceptions are being instantiated and thrown. Then we communicate instantiation of exceptions with system properties. That can be deployed with special annotations that are part of the framework. It can also be auto-deployed, almost refactoring free as a service. So there's a certain way in JUnit 5 to deploy extensions where you just have to have a library with the extension and the class path, set a system property, and then the system property will automatically look for plugins in the classes in the class path. So you don't have to touch actual code to do this. You only have to change the system property, let's say in a Maven or Cradle build script for a project. Yeah, that's really what this is all about. So that's the auto deploy option. I already explained this. Moving on to the validation of this. So we looked into a couple of projects and we measured precision and recall. So basically, our baseline is we have no sanitization, so we don't use Saflate. We use the project as we find them, and we are looking for errors that succeed when the network is on and result in failure or error if the network is off. And then we sanitize, and with sanitization we look for tests that fail when or result in error when the network is off, but at the moment we sanitize them, the state transitions into skip. And then based on this, we look into how much what we find is real, that's this precision ratio, and recall how much of what we find, of we want to find, do we actually find, that is recall. There are some limitations here. So something has to do with concurrent test execution. Maybe I can talk about this in the answer section if people are interested. So concurrent test execution might create both false negatives and false positives. We have some engineering solution to this that addresses this to some extent. Another problem that creates potential false negatives is that sometimes the instantiation of the exception and the throwing of the exception happens in native methods, for instance, in this one over here. And that's something we currently don't capture with our instrumentation. Main results are here. So we have those 6 programs. We did a search on GitHub for indication and issue tracking systems, whether there is flakiness or test failures due to network errors. So we found those. They are all fairly well-known mainstream programs. They have a reasonable high number of tests, maybe with the exception of the last one. At least 3 of them have a reasonable number of errors or failures when the network is being switched off. So BioJava, JabRef, and PDFbox. You see sometimes really just the error being propagated. Sometimes it is just the error being caught somehow in the framework and then translated into a test failure by the tests of the respective programs. And here we have, with our method now being applied, there's also, by the way, an artifact that shows this in action. We have the measurements of precision and recall for 4 of the programs. That is perfect. And for the others, it's very, very high. And the reasons for those are discussed in the papers that really relate to the limitations mentioned here. Tool availability, source code is on GitHub. The JUnit 5 extension and the JUnit 4 rule are deployed in the Maven repository. You can have a look here. Future work, well, apply approach to other scenarios. In particular, we want to model environmental dependencies here. We want to infer those annotations that can be used for this approach and maybe use Saflate there as well. And that was really it. Thank you for your attention, and yeah, hopefully we will have a chance to discuss questions you might have on our approach. Thank you so much for listening.